Hello, my name is Uriah First from the Department of Mathematics at University of Haifa, and I will tell you about a joint work with Tali Kaufman from the Department of Computer Science in Bar-Ilan University. It is about cosystolic expansion of sheaves on Posets and why they are useful to locally testable codes. So let me begin by recalling what are locally testable codes. So let's see in sigma to the n be some error correcting code. As usual, the alphabet sigma is fixed and n goes to infinity. So I'm really considering a family of codes. So informally, I say that T is an LTC, a locally testable code, if we can tell with high probability whether a word is very far from C by probing just a few of its letters. Formally, what we're really after is a Q-query tester for C with some positive soundness mu, which is just a randomized algorithm that takes a word in sigma to the n as input. It reads at most Q letters from that word, and it outputs either accept or reject. And the requirements that we want from that algorithm is that every word in C is accepted. And if a word is not in C, then the probability that we will reject it is at least mu times the distance from W to the code. So if we're further away from the code, the probability of rejection is higher. And we say that C is an LTC if it has a Q-query tester with positive soundness mu. So remember that n goes to infinity, so I have an infinite family of such codes, all of which have the same Q and the same U. Great. And local decimal codes are mainly motivated by probabilistically checkable proofs, PCPs, but they're also useful just for communication because you can decide quickly whether or not it is worth to decode the word. Maybe you can tell quickly if it was significantly corrupted. It has been open for a while whether there is a good LTC, i.e. a good LTC, an LTC with constant rate and linear distance. And just to note, if I take a random LDPC code, low density parity check code, it is well known that such codes are good codes. And they have an obvious tester, which just takes one of the low density parity checks and, well, checks them. But this is almost never an LTC. So random constructions usually don't work. And this question has been open because of that reason for a while until in 2021, two groups independently solved it. It was a breakthrough. Dinur, Avralivne, Lubotsky, and Moses, and Pantelev and Kalachev. And I should say that Pantelev and Kalachev also obtained quantum CSS codes in the same work. So I want to give you the history of that work, and then I will be able to explain our contribution. So some history. So in the 90s, Sipser and Spillman observed that you can use expander graphs to get good codes. Those are the famous expander codes. And in the early 2000s, there began a trend of studying high-dimensional expanders. And it was expected that in much the same way that expander graphs could give rise to good codes, high-dimensional expanders should give rise to good LTCs. But it was not immediately clear how. And so the journey begins. And one of the first kinds of high-dimensional expanders that was studied is coboundary expanders. It was studied by Liniel, Meshulam, and Valach, and also by Gromov. Their purposes were entirely combinatorial. Gromov wanted to study how much overlap is forced by mapping a d-dimensional simplicial complex into a d-dimensional Euclidean space. And he showed that if you have large coboundary expansion, then there is a lot of overlap. And this was sensational, and also people found it hard to understand that work. And when they studied it, they wanted to extend the reach of those techniques. This is how they came up with cosystolic expansion. Coboundary expansion is quite rare. Cosystolic expansion is more common. And it was presented as a relaxation of coboundary expansion. And it was quickly observed by Lubotsky and Kaufman that cosystolic expansion is really kind of property testing. And roughly at the same time, there were a bunch of works that gave effective criteria for constructing cosystolic expanders. I've listed some of them below. So this is a kind of property testing. So we can ask whether or not this gives LTCs. And the answer is that it does give LTCs. However, they either have poor rate or poor distance, unfortunately. And despite all this intricate mechanism, it was still not clear how to get good LTCs. And this is how things settled for a while. It was clear that one needs high-dimensional expanders with some extra structure, but it was not clear what exactly. And as I've told you, the breakthrough came in 2021 with the works of the LLM and PK, Pantalov-Klachev. They used the so-called double Cayley complexes and somehow bypassed this entire mechanism and just got good LTCs out of nowhere like magic. And what we did, is basically kind of bridging this gap, right? This entire mechanism was bypassed. And what we do is showing that really the codes of the LLM are really a consequence of cosystolic expansion. So how do we do that? Oh, I should say that these two codes are essentially equivalent. I forgot that. Okay, so we consider sheaves on posets. Those are the high-dimensional expanders with extra structure that we use. There is a notion of cosystolic expansion of sheaves, which generalizes the earlier cosystolic expansion I spoke about, and it is a kind of property testing. We show an almost local criterion for cosystolic expansion of sheaves on posets. It generalizes significantly the known criteria. And what's more important, that when applied to the right sheaf on this double Cayley complex, it gives good two-query locally testable codes. And in fact, they're not entirely new. They're actually the line codes of the LLM. So we actually recovered the LLM, and also vice versa. Those two constructions are essentially equivalent in some sense. However, our criterion is also useful for other stuff. We get local criteria for a lifted code to be an LTC, and we also recover other testability results. So it has other usages. And now I want to tell you a little about what are sheaves on posets and what is cosystolic expansion, and what does our criteria say and how it can be applied. Okay, so posets. So a poset is just a finite partially ordered set. Our posets will also carry a dimension function, taking integer values, and we insist that there is a unique smallest face of dimension -1, and some other structure that I will not talk about. The main examples are simplicial complexes and cube complexes, and more generally, you can use any regular cell complex. So here is a picture of such a complex, basically a construct of vertices, edges, and faces. And we can reorganize that into layers, so vertices in dimension 0, edges in dimension 1, and so forth. And we also have to add an empty face of dimension -1. So this is how I think about this thing as a poset. What are sheaves? Well, a sheaf is really a linear algebra layer on a poset. So a sheaf curly F on a poset X, it will consist of the following data, an F2 vector space curly F of X for every element X in X. And we need a linear map from curly F of X to curly F of Y whenever X is smaller than Y. So this linear map is called a restriction map. And these things cannot be chosen arbitrarily. There is a requirement, a coherence condition, which says that if we go from curly F of X to curly F of Y via our linear transformation, and then we go from curly F of Y to curly F of Z, then it's the same thing as going directly from curly F of X to curly F of Z. And here we assume that X is less than Y, which is less than Z. So how might a sheaf look like? Well, here is the poset from before. So the sheaf would basically just be a bunch of vector spaces, which I drew here, and a bunch of linear transformations. I drew some of them. I drew those that cross between consecutive layers. There are other linear transformations, like going directly from here to here, but they're just compositions of those maps which I drew. So it's just a bunch of vector spaces and linear transformations. Okay, so what does all of this have to do with codes? We can actually get codes from sheaves in a manner which is similar to getting LDPC codes from hypergraphs. And how does that work? So again, X is a poset and curly F is a sheaf, and I fix some integer k. Let xk be the elements of dimension k in X, and let ck be the space of ensemble Wx with X ranging on the k dimensional faces of X, where each Wx comes from the vector space associated to X. This is what mathematicians just call the Cartesian product. of those spaces. And this is known as the space of K cochains. Now, there is a linear map from CK to C to the K plus 1, and I will define it by illustration. So here is the poset. I will assume that K is 0. This is the poset from before. And what is an element of C0? It's just, I choose a vector in each vector space. Here I have the f of K, f of B, f of C, and so forth. I just choose a vector in each of them. And I want to produce a vector, an element dw in C1, so it's just choosing a vector for every one-dimensional face. And remember, I have all those linear maps going between those spaces coming from the poset. Now let's just focus on dw of little f. I have two linear maps coming to this face f, one from A and one from B. So what do? I just apply these two linear maps to WA and WB. So I apply, and I just add the sums of the contributions, and this is an element of curly f of f, and this is how I get this coordinate. And I do this everywhere. And here's a fun fact. If I apply d twice, so I go from dimension 0 to 1 and then to 2, I get 0. And why is that? So let's look at d of w at some two-dimensional face m here. And let's see, what does the face E, for instance, contributes to that thing? Well, I can go in two different ways up, right? So I can go like this and I can go like this. However, because of the sheaf requirement, this is just like going directly from E to M. So these two contributions will cancel each other. And this is why I'm going to get 0. This is actually important. So let zk be the kernel of D, i.e. all the words W and ck such that D of W is 0. This is known as the space of K cocycles. Suppose further that there is some vector space sigma such that f of x is sigma for all k-dimensional faces. So on dimension k, I only see sigma. So in this drawing, let's say k equals 0, so I only see elements from sigma in all those coordinates. So C naught is basically just sigma to the x naught. And in general, I will have that ck equals sigma to the xk. And so zk will be a code inside sigma to the xk. And moreover, notice that this code is basically defined by sparse constraints, right? Each of those faces, k-dimension, the one-dimensional faces here define the constraints that determines z naught. So there is a natural tester for that. Just take a k plus one-dimensional face at random and just accept your word if and only if dw is 0 at that face. And is this an efficient tester? Well, by definition, the Cosystolic expansion of the K Cosystolic expansion of f is the maximal soundness of this tester. And so, and the K coboundary expansion is the same thing, but we add another technical assumption, which is that the kth cohomology of x with f is 0. I don't want to go into that, but it's a much more restrictive condition, but it's essentially the same. So basically, K cosystolic expansion is a kind of, well, local distability, as you can see. So what does our criterion say? So again, x is a poset, f is a sheaf, and k is some number between 0 and the dimension of x minus 2. So I need 2 more layers above the kth layer in x. Theorem, an informal version. Suppose that x is not too wild. And 1, the restriction of f to every proper link of x has large coboundary expansion. What is a link? I drew here some example of a poset x, and there is this special vertex z. So the link of x at z is just all the faces that are larger or equal to z, just this tiny piece. And we can restrict f to that tiny piece. And basically, if on tiny pieces like that, f has large coboundary expansion, then condition 1 is satisfied. So this could be summarized as local testability. So just on tiny pieces, we have local testability. And the second condition is that some graphs associated with x and its links are good expanders. Basically, x is a high-dimensional expander. Then under these assumptions, f has large k-cosystolic expansion, i.e. zk is an LTC, the space of k cocycles. And by applying this to a special poset x and a special sheaf f, we get good two-query LTCs and some other applications. So thank you for listening so far. This is the end of my talk. And if you want to stay, there is a bonus slide in this recorded version in which I will actually tell you what is the good to query LTC that we get. So buckle on. The ingredients are the following. We need a group G. We need two generating sets, A and B, for the group G, and they have to be symmetric, meaning that if I just invert all the elements in A, I just get the same set, and same for B. They don't have to be of the same size. I need two linear codes, C of A inside F2 to the A, and CB inside F2 to the B. It's a typo here. And I should say that the size of G will go to infinity, but the cardinalities of A and B, as well as the codes CA and CB, will remain fixed. Okay, so just the group will, only the group will essentially change. So those are the ingredients. And what is the code? Well, the alphabet of the code is the tensor code, CA tensor CB. So it's a huge alphabet. What is the tensor code? It's just the R by S matrices with rows in CB and all columns in CA. So it's a subset of the R by S matrices over F2. But I would rather think of it as the subset of matrices whose rows are indexed by A and whose columns are indexed by B. Okay, so those are kind of A by B matrices over F2. And my code C can now be described as follows. So it's a subset of sigma to the G. So for every element of the group, I choose such a matrix in the tensor code. And it consists of ensembles such as these, which satisfy the following assumptions. The 8th row of MG, it's a matrix, remember, is the A to the negative 1st row of MAG. Remember that the rows of M are indexed by elements of A. And I need a similar condition on the columns, so the bth column of MG equals to the B to the negative 1st column of MGB. This has to hold for every A, B, and G. Now, notice that all these constraints involve only two letters, right? And there is a natural two-query tester here. Just choose such constraint at random, one of those at random, and just check it. Check that it holds. And theorem, suppose that that the relative distance of CA and CB is at least epsilon, that the tensor code CA tensor CB is an epsilon agreement testable. I will not define this, but it is equivalent to robustness of the tensor code. In addition, assume that the Cayley graphs of G associated to the generating sets A and B are excellent expanders. How good? Depending on epsilon. Let me not go into this. Then this code C containing sigma to the G is a good two-query LTC with that tester. And how does the proof go? We basically apply our criterion. So we realize C as the code of 0 cocycles of some poset F and a sheaf. So the poset is really the double Cayley complex of G and A and B. And it turns out that assumptions 1A and 1B, they really imply that curly F has large coboundary expansions on the proper links of X. So there will be local testability. This is 1B is really an assumption of local testability. And condition 2 really means that H is going to be a high-dimensional expander. And then you simply apply our criterion and immediately get that result. So this, to conclude, we get, by a further manipulation, we get the LLM using Cosystolic expansion and our criterion. Thank you for listening to this, and I hope to see you at the conference.